NASA's longest-running mission has achieved the unimaginable after 45 years in space. This extraordinary spacecraft has left an indelible mark on space exploration, traversing our solar system and beyond. Despite its memory being 3 million times smaller than a standard smartphone, the Voyager probes have remained at the forefront of space exploration. As Voyager 1 approaches the twilight of its operational tenure, it has made a groundbreaking discovery that promises to revolutionize our understanding of space. What exactly has Voyager 1 found? Could the fate of this pioneering spacecraft be influenced by extraterrestrial forces? Let's delve into how Voyager 1 has defied the odds and made remarkable discoveries over its 45-year journey through space. Voyager stands as a testament to human curiosity and ingenuity, significantly advancing our knowledge of the universe. Initially tasked with exploring our solar system, the Voyager probes surpassed all expectations, venturing into uncharted cosmic territories. Voyager 1's Odyssey has captivated scientists worldwide, offering invaluable insights into the cosmos. Half a century since its historic launch, the Voyager mission remains unparalleled as the longest continuous mission undertaken by any space agency. It's truly awe-inspiring how this spacecraft has exceeded its projected 5-year lifespan, challenging initial predictions. Yet, what often escapes public knowledge is the significant hurdle Voyager 1 faced during its launch. A malfunction in one of the rocket stages threatened to derail the mission, necessitating urgent last-minute adjustments to avert disaster. NASA's dedicated engineers swiftly intervened, leveraging their expertise to rectify the issue and ensure Voyager 1 could join its twin probes in space. However, as Voyager 1 celebrates decades of fruitful operation, it confronts a perplexing challenge, one that eludes conventional explanation. Join us as we probe into the intriguing possibility of extraterrestrial involvement and untangle the enigmatic circumstances surrounding this startling revelation. Before delving into the captivating specifics, let's establish crucial context. In the 1960s, following the United States' setback in the robotic moon race against the Soviet Union, space exploration underwent a transformative shift. While lunar and space dominance remained compelling, attention shifted towards a more popular and well-funded manned program. Meanwhile, unmanned exploration assumed a supportive role, with missions like Ranger and Lunar Orbiter laying the groundwork for future Apollo endeavors. Yet, the allure of exploring other planets captured widespread imagination, ranking second only to the excitement surrounding the Apollo missions. Consequently, unmanned exploration programs naturally evolved towards the logical progression, exploring other celestial bodies. Reflecting on the past, some individuals tend to exaggerate the scientific significance of unmanned programs when compared to the political and technological ambitions of manned flights. They contend that robotic missions were inherently more focused on scientific purity, inadvertently diminishing the scientific accomplishments of manned missions. However, what truly captured the imagination and ignited public passion was the promise of capturing images of the planets. It was the prospect of witnessing these visuals that stirred the greatest interest and enthusiasm during the heyday of space exploration. On September 5, 1977, an awe-inspiring spacecraft embarked on its journey from Cape Canaveral, Florida, renowned for its role in testing missiles and space probes. This momentous occasion marked the commencement of an extraordinary odyssey as Voyager 1 ventured into the vastness of space. Intriguingly, a mere 15 days prior, its counterpart, Voyager 2, embarked on a parallel cosmic voyage. Their primary objective was to explore the gas giants of our solar system, Jupiter and Saturn, alongside their numerous moons. Little did anyone anticipate that these fearless adventurers would surpass their initial objectives and journey to the farthest reaches of our celestial neighborhood. Equipped with state-of-the-art technology, even by the standards of their era, the Voyager twins boasted meticulously designed engines, propellers and antennas, all engineered for resilience and endurance. NASA took inspiration from the Mariner spacecraft but infused intriguing modifications into the design of the Voyager probes. The achievements of these probes have been truly remarkable. Over 40 years ago, their initial observations of Jupiter and Saturn's moons astonished researchers and shattered previous assumptions about these distant celestial bodies. What were once thought to be barren and cratered surfaces, akin to our own moon, turned out to be vibrant with geological activity. Voyager 2, in particular, reached several significant milestones during its journey. In 1986, it became the first spacecraft to pass by Uranus, followed by a flyby of Neptune just 3 years later. To date, Voyager 2 remains the only spacecraft to have ventured on such a trajectory. As these spacecraft continue their extraordinary voyage, NASA has taken measures to prolong their operational lifespans. Over the past 3 years, non-essential components and heaters have been deactivated to conserve energy. This strategic decision ensures that the Voyagers can continue operating well into the next decade, with their mission estimated to conclude in 2030. For the scientists and engineers who have been integral to this remarkable journey from its inception, the conclusion of the Voyager missions evokes mixed emotions. Their steadfast dedication and tireless efforts have propelled the project far beyond its initial goals. The data transmitted by the Voyagers has provided invaluable insights, leading to numerous scientific breakthroughs and inspiring generations of researchers and space enthusiasts alike. It's worth emphasizing that Voyager 1 and Voyager 2 weren't your run-of-the-mill spacecraft. They were meticulously engineered to serve as stable platforms, with a rotation rate more than 15 times slower than the hour hand of a clock. This deliberate design ensured minimal blurring of images and data as they traversed through space. Their remarkable imaging capabilities never failed to captivate both scientists and the general public, even before their encounters with the outer planets. Months before reaching Jupiter, the spacecraft began transmitting images back to Earth, showcasing the mesmerizing swirling clouds and the iconic Great Red Spot. These early glimpses brought sheer delight to the team at NASA's Jet Propulsion Laboratory. However, it was the discovery of active volcanoes on Jupiter's moon, Io, that truly stole the spotlight. Despite being just slightly larger than Earth's moon, Io emerged as the most volcanically active body in our solar system. The spacecraft's instruments picked up peculiar signals emanating from Io, with vivid images confirming the presence of towering volcanic plumes and a surface scarred by volcanic activity. One of Io's notable volcanoes, Pele, erupted nearly 30 times higher than Mount Everest, covering an area almost the size of France with volcanic material. In total, the Voyager spacecraft captured over 33,000 images of Jupiter and its moons, unveiling the planet's breathtaking beauty and the diverse landscapes of its moons. Before we delve into the recent astounding discovery, let's remember that the Voyager twins have been unraveling remarkable findings since their launch. One of the most astonishing revelations was the existence of Jupiter's faint rings, adding an extra layer of intrigue to the gas giant. Furthermore, Voyager 2 revealed the icy shell encasing Europa, one of Jupiter's 53 named moons, estimated to be over 60 miles thick. These discoveries challenged our prior assumptions about these distant celestial bodies and ignited further investigations into the potential habitability of icy moons. As the Voyager probes bid farewell to Jupiter, they received a crucial gravity assist that provided them with a vital boost, propelling them towards Saturn. This clever maneuver was essential for them to escape the gravitational pull of the Sun and venture deeper into space. Subsequently, Voyager 1 and Voyager 2 embarked on divergent paths, each heading towards new horizons. Voyager 1 journeyed along a trajectory that brought it close to Saturn's moon Titan, shrouded in an orange, hazy atmosphere. The enigmatic nature of this moon intrigued scientists, prompting extensive studies on its intricate chemistry. Voyager 1 then veered northward, departing from the plane of the planets, commencing its epic odyssey beyond the boundaries of our solar system. Meanwhile, Voyager 2 embarked on a series of thrilling expeditions to the outermost planets of our cosmic neighborhood. In 1986, it made history with a flyby of Uranus, where it stumbled upon 10 previously undiscovered moons, augmenting the planet's moon count. 3 years later, Voyager 2 reached Neptune, unveiling the extraordinary features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds of up to 1,000 miles per hour, marking it as the fastest wind ever observed on a planet within our solar system. As the spacecraft zoomed within 2,980 miles of Neptune's azure methane-rich atmosphere, it provided unprecedented insights into this remote world. Neptune's largest moon, Triton, emerged as one of the coldest locations in our solar system, with surface temperatures plummeting to a bone-chilling minus 391 degrees Fahrenheit, minus 235 degrees Celsius. Triton showcased distinctive features, including ice volcanoes ejecting nitrogen gas and icy particles soaring up to 5 miles high into its sparse atmosphere. These findings broadened our comprehension of the remarkable diversity and intricacy of celestial bodies, even in the remote realms of our cosmic vicinity. One individual who significantly influenced the extension of the missions beyond their original objectives was the esteemed astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he fervently advocated for capturing a final set of images before deactivating the cameras on both spacecraft. These images would serve as a farewell gift to humanity, offering a poignant glimpse of our home planet from the distant depths of space. Sagan's perseverance bore fruit. On Valentine's Day in 1990, Voyager 1 turned its camera back towards the inner solar system and snapped a series of 60 images. Among them, the most iconic is the pale blue dot, etching itself as a timeless symbol of our existence in the cosmos. Taken from an astonishing distance of 3.8 billion miles, it stands as the farthest image of our planet ever captured, portraying Earth as a faint pale blue speck barely discernible amidst the vast expanse of space. At the heart of the Voyager mission lies an extraordinary relic, the enduring 8-track tape. Picture it as a time-traveling artifact, a repository brimming with invaluable scientific data hurtling through the cosmos. The 8-track tape recorders utilized on the Voyager probes differed significantly from typical consumer cartridge tapes. They employed a reel-to-reel storage system designed by Lockheed and manufactured by Odetics Corp. These machines boasted impressive specifications, featuring a belt-driven mechanism and utilizing a 1076-foot, 328-meter, long reel of 1 2-inch, 12.5mm wide magnetic tape. The tape consisted of 8 distinct tracks for data recording. The recorders offered 2 different recording speeds, 115.2 kilobits per second, kbps, and 7.2 kilobits per second. During playback, the maximum speed was slower at 57.6 kilobits per second, with options also available for 33.6, 21.6, and 7.2 kilobits per second playback speeds. Now, you might be curious as to why there are only a few missions as successful as the Voyager mission. It's time to explore that question. What strategies were employed to ensure the success of the Voyager missions? Nearly 50 years ago, in August and September of 1977, a team of humans launched a pair of robots to explore the solar system and delve into the infinite darkness beyond. To accomplish their objectives, these intrepid spacecraft utilized a clever technique known as gravity assist maneuvers, which played a pivotal role in their legendary journeys. Think of it as a cosmic ballet between the spacecraft and the massive planets of our solar system. Instead of solely relying on their own propulsion systems, the Voyagers harnessed the gravitational pull of these colossal planets to propel themselves towards their destinations. This ingenious maneuver not only conserved fuel, but also imparted the necessary velocity to visit multiple destinations during their grand tour. let's delve deeper into the intricacies. Gravity assist, also referred to as a gravitational slingshot, involves transferring some of a planet's momentum to the spacecraft as it flies by. Imagine Voyager 1 approaching Jupiter, a colossal gas giant with an equally immense gravitational influence. With meticulous precision, Voyager 1 was guided to swing by Jupiter at precisely the right angle and speed. Jupiter's gravitational pull then accelerated the spacecraft, providing it with a significant velocity boost, an essential cosmic push. However, executing this maneuver requires a delicate touch. If Voyager 1 had approached Jupiter at the incorrect angle or velocity, it could have led to a catastrophic deviation from its intended trajectory. The level of precision required for this maneuver is truly staggering. Nevertheless, the brilliant minds at NASA's Jet Propulsion Laboratory orchestrated these celestial dances flawlessly, not just once, but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on an awe-inspiring journey through the solar system. For example, Voyager 2 utilized gravity assists from Jupiter and Saturn to reach Uranus and Neptune, enabling the grand tour of the outer planets. The Voyager missions owe an immense debt to these slingshot maneuvers. Voyager 1 ventured into interstellar space, followed swiftly by Voyager 2, all thanks to the precision of these gravity assists. While the concept behind gravity assists may seem straightforward, their execution is remarkably complex. Voyager 2's grand tour demanded meticulous precision, as missing any of these slingshots could have spelled disaster. Nevertheless, the individuals behind these missions remained steadfast in their quest for knowledge and exploration of the unknown. While gravity assist maneuvers played a pivotal role in navigating the cosmos during the Voyager missions, another crucial element ensured their success: the Deep Space Network, DSN. Think of it as the interstellar communication line that maintained essential contact with our intrepid Voyager probes as they ventured into uncharted territory. So, what exactly is the Deep Space Network? It may not have the glamour of a spacecraft, but its importance cannot be overstated. The DSN comprises a network of colossal radio antennas strategically positioned around the globe, with locations in California, Spain, and Australia. These immense antennas, ranging from 26 meters to an impressive 70 meters in diameter, serve as celestial loudspeakers, enabling communication with spacecraft beyond our planet. The Voyager missions have played a crucial role in inspiring numerous remarkable expeditions into interstellar space. However, before we explore the groundbreaking discoveries made by Voyager 1, it's essential to highlight the significance of other remarkable missions: Pioneer 10, Pioneer 11, and New Horizons. These missions have greatly contributed to our understanding of the solar system and beyond. Pioneer 10, launched on March 2, 1972, marked the first spacecraft to venture beyond the asteroid belt and explore the outer solar system. Its primary objective was to conduct flybys of Jupiter and its moons. On December 3, 1973, Pioneer 10 achieved the milestone of becoming the first human-made object to traverse the asteroid belt, providing valuable insights into this region of space. It then performed a close flyby of Jupiter, capturing breathtaking images and gathering crucial scientific data about the gas giant, its atmosphere, and its moons. Pioneer 10 continued its journey beyond Jupiter, becoming the first spacecraft to cross the orbit of Neptune in June 1983. Despite losing contact with Earth in 2003, Pioneer 10 remains the first man-made object to exit the solar system, venturing into interstellar space. Following in the footsteps of Pioneer 10, Pioneer 11 was launched on April 5, 1973, with similar objectives. It successfully completed a flyby of Jupiter on December 2, 1974, capturing stunning images of the planet and its iconic Great Red Spot. Pioneer 11 then embarked on an extended mission to explore Saturn and its moons, On September 1st, 1979, it achieved the milestone of becoming the first spacecraft to conduct a flyby of Saturn, offering unprecedented views of the planet's majestic rings and gathering essential scientific data. The mission also unveiled new insights into Saturn's atmosphere and its moon Titan, revealing a thick, nitrogen-rich atmosphere and hints of potential organic chemistry. Pioneer 11's successful journey to Saturn significantly enhanced our comprehension of the gas giants in our solar system and their diverse moons. Shifting to a more recent endeavour, New Horizons was launched on January 19, 2006, with the primary objective of studying Pluto and its moons. After a 9.5-year voyage, New Horizons executed a historic flyby of Pluto on July 14, 2015. The mission delivered the first detailed images of Pluto's surface, uncovering a complex and geologically active world adorned with mountains, plains, and icy terrains. New Horizons also unveiled unexpected features such as Pluto's hazy atmosphere and signs of flowing nitrogen ice. Following its triumphant encounter with Pluto, New Horizons continued its trajectory into the Kuiper Belt, where it conducted a flyby of a small, icy celestial body named Ultima Thule on January 1, 2019. This encounter provided invaluable insights into the formation and evolution of objects in the outer reaches of the solar system. Having witnessed these remarkable interstellar endeavours, let's now delve into the extraordinary discovery made by Voyager 1 in interstellar space. What fascinating discovery did the Voyager probe uncover in interstellar space? During their interstellar odyssey, the Voyager probes confronted a significant milestone known as the heliopause, the boundary separating the Sun's influence from the vast expanse of interstellar space. The exact location of this boundary had long been a subject of debate. But thanks to astronomer Bill Gurney's projections in 1993, it was estimated to lie between 116 and 177 astronomical units, AU, with each AU equivalent to the distance between the Earth and the Sun. Gurney's estimations proved precise when Voyager 1 reached the heliopause approximately 2 decades later, detecting the anticipated rise in plasma density. However, an intriguing puzzle emerged. Despite the observed increase in plasma density by Voyager 1, there was no significant alteration in the direction of the ambient magnetic field. This outcome was unexpected because a transition from a region where the magnetic field originated from the Sun to one where it was sourced from other stars should have resulted in a noticeable deviation. Adding to the puzzle, Voyager 2 reached the heliopause at the same distance as its counterpart, but failed to register any changes in the magnetic field. These unforeseen findings presented challenges to the theoretical models portraying the behavior of the heliosphere and its interaction with the interstellar surroundings. The anticipated synchronization between the heliosphere and the Sun's 11-year cycle did not align with the data collected by the Voyager probes. Moreover, the solar wind, which fluctuates with the Sun's cycle, was at its peak when Voyager 2 arrived at the heliopause, suggesting that the projected position of the boundary should have been farther out than 120 AU. Nonetheless, the data amassed by the Voyager probes have played a vital role in refining theoretical models. Scientists now hypothesize that our Sun has transitioned from a hot, ionized zone to a partially ionized region of the galaxy, likely triggered by nearby supernovae. These ancient exploding stars heated the surrounding area and stripped electrons from neighboring atoms. The boundary between these regions can be likened to a turbulent seashore, characterized by mixed magnetic fields and small-scale changes near the heliopause, while larger-scale variations are negligible. Regarding the future trajectories of the Voyager probes, Voyager 1 is headed towards the constellation Ophiuchus, while Voyager 2 is bound for the constellation Cetus. While some scientists anticipate a cosmic demise for the probes by 2030, they could potentially endure for millions of years, outlasting our own species. Perhaps one day they will encounter other star systems, carrying with them the golden record, a time capsule representing humanity. Thank you for joining us on another episode. While you're still here, feel free to click on the other videos you see on your screen.